Well, I took the full length yesterday and I was kind of disappointed because I did worse than I did on the first one. Um, I guess like I did, what'd you say?
Oh, let me see. So, okay, this is the, oh yeah, and then you asked me what that, I think that car score came out to 126.
Okay.
So, okay.
Cars, I
Hmm.
think I was like reading, I wasn't reading properly, I guess, because I missed a lot of the bigger concepts, like the main ideas of the passages. So then when I went back and I looked at it again, it made more sense, and I ended up getting a lot more of them correct. Bio, I haven't done the blind review yet because I've been working on chem and I'm almost done with chem. That one too, I did 1 point higher than I did the first one, which I guess is good. But there's I think stuff where I see the question and then I don't like connect the details from the passage. That could be like a really easy thing and then apply it to the question. So then I'm like trying to find all of this extra knowledge that I like might not have and I get flustered.
Got
Um,
it. So for this test, was there like, did you get not enough sleep perhaps, or did you feel off?
I mean, I was kind of stressed out the morning of well, yesterday I had like medical school like cycle orientation thing, and so I was talking about it with my mom in the morning and she kind of stressed me out about
Yeah.
it. Um
Uh-huh.
so I guess like I could have been a little bit off
So like
because
talk to your mom about this stuff like before your test, you're saying?
yeah, like half an hour
Uh-huh.
before.
I see, I see.
So
Yeah.
that could have been a problem, but
Mhm. Got it. Yeah, so you were saying that when you're reading your car's passages that you weren't like completely like, getting like the main the
yeah, I mean, I've noticed that that tends to happen with chem more than with cars. Like sometimes I'm still missing stuff with cars, but it was way easier for me to understand it the second time around. And then I also was testing out a new strategy afterwards.
core.
I like I decided for the blind review to just read the passage again, like kind of quickly without highlighting anything, and then try to answer the questions. And then I went back to the passage, read through it, and highlighted like key information pertaining specifically to the questions.
Wait,
And then I like
what
answered them again.
what section are you talking about?
Cars.
Cars. So you're saying what you did differently was what?
Like I basically read the passage twice. The first time was just to not look at the little details and get the bigger idea.
Okay.
And then I would answer all of the questions for that passage. And then I'd go back and like highlight things like I normally would, but what I highlight would be more catered to the questions, if
Okay.
that makes sense. I
Uh,
just don't know like if I'll be able to do that on the test, like if I'll have time to do that.
huh?
Um,
So you
but
also
we'll
said
see.
something about something being more so the case with Chem Phys than cars. What was that?
Um, Not being able to understand the bigger picture with the chemist, like the chem and physics passages still. Like I know we talked about that last week a little bit.
Hmm.
I'm still having some trouble with it.
Got it.
Um,
Okay. So yeah, we haven't done any cars together. So if you want, we can go over like a cars strategy for that. But um, but we could also go over like CP or any of the other stuff.
um, I guess I'd probably stick with chem and then I'm gonna see if like the strategy I have is gonna work for cars. Um,
Wait,
yeah.
the strategy, I thought that the strategy that you were talking about was with cars, where you read the passage and then you read the questions and then you.
Yeah, but that's like new. Like I did that for the blind review afterwards.
Mhm,
During the actual test, I was kind of sticking with my old way.
mhm. Which is typically.
Um, Going through and highlighting keywords and sometimes phrases, and then answering the questions afterwards. And I tend to like go back and forth a lot.
Got it. Okay. All right. Yep. Let's work on what you want to work on.
Okay. Um, so I guess more recently from yesterday, I have like a couple things I wanted to talk about. Okay. So this one,
Do you think you could full screen it?
yeah, one's okay. My main issue with this one was um the diagram. Oh, that's um for the reduction potential. I just had like a lot of trouble reading that and understanding what was happening. So maybe if we could go through how to read them, that would be helpful.
Like reading the passage you're saying?
No, read like specifically reading like diagrams for half reactions and the reduction potentials, like they have for figure 1 and 2.
Let's see. NADPH diagram for manganese. All right, so it seems like there's an x-axis, which is pH, a y-axis, which is your, I guess, cell potential or your half reaction potential. And let's see. Um, okay. Um, MnO2, MnO4, N2 plus. Okay, let me see what this question's asking. Based on figure 1, what conclusion can be made about the redox characteristics of manganese? Okay, so I guess we can just go through each of these. So at a potential cell potential of negative zero point 0.8, which is here, Mn2 plus exists in solution at all pH values. Well, let's see, right? So it seems to exist as the cation from pH 0 to pH around like 7.4, it seems, right?
Yeah.
After that, it gets, incorporated into these, oxides and hydroxides and stuff, right?
Mhm.
So we know A can't be true then, right?
Yeah. I was like mostly confused with C. And I mean, B, I ended up picking.
Let me see. So B at a pH greater than 4, MnO2. So 4 MnO2 over here is reduced to form at pH greater than 4. So like, to the right of this, MnO2 solid is reduced to form Mn2 plus. Uh, so we're going, this way, right?
Mhm.
At higher pHs, it doesn't seem like we're turning it into Mn2 plus, right?
Yeah. I mean, oh, okay. I guess I was reading it as like at a pH of 4. Maybe that's why I was confused with that one.
Uh,
Because like at a pH of 4, it like
uh-huh.
I don't know. I was just kind of confused.
Yeah, so at a pH of 4, it seems like it's right on the line between MnO2 and Mn 2 plus.
So if something is on the line, that means that it's in equilibrium.
Uh-huh. Yep.
Okay.
So if the pH was less than 4, this would be going this way into the MnO2. I'm sorry, Mn2 plus, right?
Yeah.
So B would be true if they were saying for pHs less than 4, right?
Hmm.
But since they're saying pHs of greater than 4, it can't be true, right?
Yeah.
Okay, so that's out. And then at pHs less than 7.4 and where I'm going to clear this and where E is negative 1.17, so that's like here, and 7.4 is like there, right? The equilibrium between, oh wait, uh oh yeah, the equilibrium between, okay, so we're doing less than the 7.4, so like basically like, like this region here, right? The
Yeah.
equilibrium between Mn solid and Mn2 plus is, oh wait, hold on, my bad. I did positive 0.17. It's negative 0.17, which is here, and pH of 7.4 is here, right? So this seems like
Hmm.
it's along, well, let's see, equilibrium between Mn solid and M. So yeah, maybe, oh, you know what? I see. So this like tick box right there, kind of hard to see, but
Oh,
like right
yeah.
there, right?
Yeah.
That's the tick box for negative 1.2, right? So this horizontal line is a little bit above that tick box. I don't know why I'm calling it a tick box, but the tick, right? You know what I'm saying?
Yeah.
So this line represents the negative, like probably represents the negative 1.17, right?
Yeah.
And that's right on this line, right? And this is the pH of 7.4. So at pHs less than 7.4, aka right on that line, it's true that Mn solid and Mn2 plus are in equilibrium, right?
Okay. And then for C, when it's saying that
Mhm.
um the Mn solid is oxidized.
Yeah, so I'm going to do the same thing. So I'm going to do it at -1, which I guess is like here, right?
Yeah.
Um, it says Mn solid. Wait, yeah, -1. pH less than 7.4. Mn solid is oxidized to form Mn like hydroxide with like the two OHs. Uh, that's not true because it's just Mn2 plus at E equals -1 volt and pH less than 7.4.
So when it's saying like where all of these molecules lie on the graph, like what would like that means that like a different reaction is happening depending on the cell potential.
So so what are you saying exactly?
I'm just confused like what the graph is really showing. Like each of these molecules is in the cell or like in the reaction, and it just depends on the cell potential of which one is
So
going
each
to
of
be
like
present.
so each of these like shapes were like this entire shape, anything that's within that is going to be your solid manganese, right?
Yeah.
So, and then, anything within this shape is going to be manganese 2 plus, right?
Yeah.
So, so you could see that for anything, right? Like, let's say that, uh, okay, let's say that we have in, I'll do like, something kind of simple, like, so for an E of negative zero point 0.8, um, if we go from pH of 6 to pH of 8, we should see Mn2 plus turning into Mn hydroxide with the hydroxide, right? So
Yeah.
that's what, yeah, that's how to read the figure.
Okay.
Mhm.
Yeah, I think like I was also confused by the like dotted diagonal lines, how that comes into play. It says that they represent the reduction potential. So
Yeah.
how is that different than the y-axis?
Well,
Like,
so that the dotted lines seem to be related to what they're talking about in the passage. So I didn't really consider them when answering this question. Um, because this question's really just asking, based on figure one, what can we say is true about the, manganese like redox? But let's see.
yeah.
In the passage they say that
I
um
guess I'm like just concerned about it because if I got another one of these graphs, like would it still have like dotted lines, or is that just something for this like passage specifically? Like, is that typical of one of these graph types?
uh so so these graph types are essentially just there to show you, you know, that if you know the pH or and um the potential, you can figure out which like oxidation form or redox form of manganese is going to be present. So but now for the dotted lines, they will be something relevant to some specific thing that's happening in that passage. So apparently, let's see. So they say that the diagonal dotted lines in figures 1 and 2 represent the reduction potential of half reactions 2 and 3. Okay? So half reaction 2 is the upper line, and this dotted line here is supposed to be like this type of whatever redox reaction. Uh,
Mhm.
and then the lower line is supposed to be representing this one. Uh, so that's just going to be relevant to the passage itself.
Okay.
Yeah, it seems like they're using so for vitiligo, which is that's what Michael Jackson had. Like, you know what that is, vitiligo?
Yeah.
Mhm.
Mm.
So there's a link between the onset of vitiligo, levels of epidermal hydrogen peroxide. Okay. So hydrogen peroxide in high amounts is caused by a reduction in a catalase brought on by oxidative stress. Elevated levels of H2O2 responsible for the bleaching of natural skin pigment, and they did some research to develop some treatments like topical containers of manganese, and the topical manganese results in the formation of MnO2, which is a catalyst of decomposition of hydrogen peroxide. So that means that high amounts of hydrogen peroxide in the skin uh is linked to the onset of vitiligo. So manganese is found to be uh to catalyze the decomposition of the hydrogen peroxide. So we can kind of destroy the hydrogen peroxide by, using a cream with manganese. Um, mhm, yeah.
Okay.
And then they say natural catalases can use iron as well as manganese. So the researchers wanted to figure out, okay, what would be better if we used a cream with manganese or a cream with iron, right? And then they looked at these EPH diagrams and they determined um, that yeah, half reaction two is that upper line in both of these figures, and then so that seems to be the peroxide getting broken apart into water, and half reaction two seems to be oxygen getting oxygen turning into the hydrogen peroxide. So that's yes, the dotted lines just represent these specific half reactions. Um, so so this EPH diagram would normally not have those dotted lines. So yeah, when you see something like that, and when you see a question like this that says just straight up, based on figure one, which conclusion can be made? Um, well, we'd have to go through each of the choices. It's hard to kind of just, look at it and tell right away what's actually happening. So
Mhm.
yeah, I would do it that way. Um, but yeah,
Okay.
in general, yeah, you wouldn't have the dotted lines, but you do referring to something specific.
All right. That makes more sense then, I guess. Um, then I have another one. Can we go through like the rules of a conjugated system, like whether something is aromatic or not? Because there was a whole passage on it, and I got a couple of them wrong, and another one I kind of just guessed. I can pull them up, but like for this one, for example.
Mhm.
first of all, I was confused on the difference between B and D. And then I also like wasn't sure whether having a positive or a more negative like carbon atom would be better and like how that built the criteria.
Okay, so when you have a negative sign, it indicates a lone pair of electrons. Whereas if you have a dot, it represents a single electron. Like that's what you would see in a free radical, right?
Yeah.
So yeah, so you have your 4n plus 2 pi electrons. And that pi electron will happen when you have a double bond. Um, so yeah, we can just count the number of pi. So okay, so we need let's see. So aromaticity or Huckel's rule requires there to be 4n plus 2 pi electrons, as well as for the molecule to be planar.
In the equation for Huckel's rule, like what does the N mean? Like what are you looking for?
Um, so uh the the so the N1 is referring to the number of those um pi electrons. Let me see. So 4n plus 2 pi. N is an integer, 0, 1, 2, etc. So here we have for benzene and
Like how did they know that it was six um P's? Like is that just because they were all sp2 hybridized?
okay, so N I think can represent the number of filled pi electron energy levels or shells in the molecular orbital associated ring. So that number can essentially vary. So like, if n is 0, this is gonna just give us 2. If n is 1, this will give us 6. If n is 2, this will give us 10, right? If n is 3, this will give us 14. So so the n value might not be readily apparent, but uh what it means is that our number of pi electrons will have to follow follow that in order to make it so that it can give you like 2 pi electrons, 6 pi electrons, 10 pi electrons, etc.
Mhm. So
So
then like there was another question too. I know we like didn't finish this one yet, but there was one that was like, oh, the next one where like it said like 10 pi electrons. Like, how did they calculate that number?
Okay, let's see. I think the easiest way that I would determine the number of pi electrons is, so we know that a pi bond exists when you have a double bond.
Mhm.
So each of these double bonds should have two pi electrons.
Okay.
So you would get 10 pi electrons total that way, like each double bond. So basically, yeah, like sure, there's the Huckel's rule, 2n plus 4n plus 2 pi electrons, but so first we're gonna look for if something is cyclic and if it's planar and if it's fully conjugated, which fully conjugated means, like double bond, double bond, which means every atom or every, carbon in the ring uh is going to participate in conjugation using through a p orbital. So, and then each double bond contributes two pi electrons. A lone pair, if there was one, could also contribute two pi electrons. And yeah, so let's see.
Like, I know nitrogen is a lot of times used for stuff like this. Like, this question,
Mhm.
sorry, I like keep skipping around, but this one like had nitrogen in the ring. And is that because nitrogen like has an extra lone pair?
Uh-huh.
So even when it's like attached to another hydrogen.
Yeah. So I should have said each atom rather than particularly carbons.
Okay.
Hmm.
So that like so I guess for like cytosine, you have the nitrogen at the top and then it's bonded to three things. So it could still have like the lone pair comes from the fact that it doesn't have that other hydrogen or like the other molecule that it's connected to. Because I like kind of get confused with nitrogen, how it's like five or I just get confused with that.
Yeah. So yeah, I would still look at one, two, three double bonds. Each double bond has two like pi, electrons, right?
Mhm.
So I'm gonna have six pi electrons here. And then here, one, two, three, four, eight pi electrons there. Wait, one, two, three, four, eight. But eight doesn't, maybe I've been doing this one wrong. One, two, three, four. The guanine is okay, planar, 10 pi electrons. What am I missing here?
When it says that
Um,
something can satisfy the 4n plus 2
L
rule.
so it so okay, yeah. What you're saying before, like so nitrogen, so this nitrogen here is like, you know, I'm just drawing the bonds for it. Three bonds, right? It'll
Yeah,
have to have a lone pair. Okay.
yeah,
So so basically a so okay, things that will be pi electrons will be so 2 pi electrons for each double bond, 2 pi electrons for each lone pair, and um 0 pi electrons for a carbocation. Uh, right, because a carbocation is when you lose your electron.
hmm
Um, and if you have and then 2 pi electrons if you have a negative charge. Okay. So for the guanine, we have one, two, three, four double bonds, which means four or 8 pi electrons there. And then this nitrogen here has a lone pair, which contributes to like that's why like you can see like partial double bond character and stuff like that. So that's going to also contribute. So that's why you'll get the 10 pi electrons for guanine. And we know those that the numbers would be like what would it be? It's like 2, 6, 10, 14. So okay, so we can so rather than trying to figure out the number of pi electrons using this equation and trying to figure out what n is, which is ultimately like not something intrinsically that we can see, like, from when we look at the structure of a molecule, we can't really tell what n is going to be.
hmm
So I think the best thing to do is like use the other stuff that I said, like to count the number of pi electrons. Like, first of all, each double bond, count the double bonds and multiply that by two to get pi electrons from the double bond. 2 pi electrons for each lone pair as well. So pay attention to, like, when a nitrogen could have, a lone pair. If there's a negative charge, like a full-fledged negative charge, that'll also count as 2 pi electrons. But if you have a carbocation, it's going to have zero, that carbocation part is going to have 0 pi electrons. So use that to figure out the number of pi electrons and then to determine if it's, aromatic or not, granted that it's both a ring and um, planar, right? If it then has the correct number of pi electrons, right?
hmm
Which means either 2, 6, like that's where this equation comes in because it gives you uh possible numbers for pi electrons in order for something to be aromatic.
Okay.
Mhm. So
Mhm.
yeah, so count your pi electrons through other means and then see if it follows the 4n plus 2 rule. So like that means like so if you ended up with like when I mistakenly wrote 8 pi electrons, if something has 8 pi electrons, it's not aromatic.
Okay.
You use that to check if something's aromatic or not.
So then for this one, it's not like could you explain A as an answer choice? Like no p orbitals are available. When would that be? Like when is that seen? Like when you have an sp3?
Yeah, if you have like a carbon single bond, um, and you just have overlap of the S, um, or rather your what is it? Your orbitals, S orbitals, um, are going to be like so like yeah, so okay, if you have a single bond, you would have your S orbitals overlap like this, right?
Mm-hmm.
And if you had a double bond, like in addition to these, you will have these p orbitals overlap, right?
Okay.
So, and then your triple bond would have, the sigma and the p's, but like p in like the y axis, p in the z axis. So you're going to have even more p electrons. So yes, for if it says no p, like if you're gonna start using p uh orbitals when you have your double bond or your triple bond.
So like if you see a double or triple bond, that's how you would know that that answer is wrong.
Yeah.
Okay. And so as the correct answer is saying that the hydrogens are sterically hindering the molecule. Um, I guess I'm like wondering why that is
Hmm.
because couldn't that like why are the hydrogens pointing inwards? Like couldn't they be pointing up or like out?
Hmm. Okay, let's see. So, um, conjugated ring system that is not aromatic. And okay, so each of these carbons should be bound to a single hydrogen. And I'm also kind of thinking of this like be like having like a shape of like a chair, like, but I mean, okay, so the could mess with the it being planar. Um, let's see. Hydrogen atoms oriented in. So okay, first I'm gonna just look at C. So it includes two trans uh double bonds, which are forbidden in aromatic molecules. Well, cis or trans won't be forbidden in aromatic molecules, right? Because the only conditions we need is, planar, ring, satisfy Huckel's rule for the number of pi electrons. So doesn't matter if it's cis or trans. Uh,
Mm-hmm.
but it doesn't seem like these are any, let's see. Oh, it has like, okay, like I guess these are cis, these are cis, this is trans. So we see both cis and trans. Uh, yeah, we do see two trans double bonds, but they're not forbidden in aromatic molecules, so we can get rid of that. And then last one, there are only 10 pi electrons available for delocalization. So that would be the reason for it to be aromatic, right?
Mm-hmm.
So, we're being asked why it's not aromatic, so we can get rid of that. And then the hydrogen atoms oriented into the ring sterically hinder a planar conformation. Okay, so, let's see, we have a hydrogen here, hydrogen there, there, there. Oops. Yeah, okay, so um
Like, is there a reason why the hydrogens in the center can't just go like straight up on the page and then straight down? Because wouldn't that still be planar?
I think it gets the issue comes from like so this so okay, so since these are all sp2, hybridized stuff, like the angle of the hydrogen would be like 60, 60 degrees, like it's going to be like that kind of shape,
Yeah.
right? So like that would mean that would mean that, in this direction would be a hydrogen. And then for this one over here, this direction should be a hydrogen. This should be a hydrogen. And then that should be a hydrogen. That hydrogen, that hydrogen. And then here again, we have IC. So these hydrogens are like right in each other's faces, you know?
Okay.
Hmm.
Oh yeah, I guess I was looking at it not as like the opposite of the bond. I just like was looking at it weird.
Yeah.
Um,
So when I first looked at it, I was like, well, it should be aromatic, or if benzene works as being aromatic, and I looked at this and I thought it looked like just two benzenes, so I was trying to think, okay, like, all right, then what can be the like issue here? But where like where they connect, like the two benzenes or whatever connect, that's where
mhm,
the issue rises, because that's when you have like the hydrogens just, pointing towards each other. So yeah, so what I would do to answer this question is so first I would count the number of pi electrons by counting the number of double bonds. So I get 1, 2, 3, 4, 5 times 2, 10 pi electrons. So which means which is a okay amount of pi electrons to have for aromaticity. So
mhm,
D I would go to and cross out, because D says that there are 10 pi electrons, which is true, but that should make it aromatic rather than non-aromatic. So I'd get rid of
gotcha.
that. Um, and like even before that, I can get rid of A, because they're saying no p orbitals are available, but you're gonna have a p orbital available anytime you have, a double bond or, triple bond and stuff. So we see double bond, so that's gonna be out. And then I would see D, it says it includes two trans double bonds, which are forbidden in aromatic molecules. Again, I would remember aromatic molecules. What do we need in order for it to be aromatic? Planar, ring, satisfied, Huckel's rule for the number of pi electrons. So
Mm-hmm.
no rule states that trans double bonds are forbidden in aromatic molecules, so I get rid of that. And then like B, because even if so three things. Like I went over like how it would be like steric hindrance here. So that's one reason, like the actual reason. Uh, the second way of approaching it would have been obviously through process of elimination. But then the
Mm-hmm.
third one would be like, okay, like it like if this was the case, like does that like follow the rules? If you hinder a planar conformation, does that make something non-aromatic? It does, right? It makes if something because aromaticity requires it to be planar. So whatever it is that causes it to hinder the planar conformation, like is less important than just the fact that if you hinder a planar conformation, you're going to get something's going to be not aromatic.
Okay. And then, so then again, like for this one, because you have six um pi electrons, it works. And because it's planar,
So yeah, going through each of these. So A, we have an sp3 atom here, right?
yeah.
Which means so that this carbon here has, two double bonds and two hydrogens, right? And
Yeah.
that removes its plane, it makes it no longer planar, right?
Hmm.
Is well, really this would be like going whatever, like into the page, out of the page, right?
Okay.
So so because remember like how like sp3 is like for like single bonds. Like if you have an sp3 carbon, it's going to be bound to four things. Like which means single bonds to four things, and that would have like, a tetrahedral geometry or something like it. Whereas,
Got
yeah, a double bond would give you your trigonal planar shape
Okay.
like this. Um, and your and so this would be sp2. And then sp3 would be like a triple bond, which would be like, you know, a linear shape.
Hmm.
So okay, so A has an sp3 carbon, which is not planar, so that's out. And then when we talked about the um the free radical, like single electron here, like because we're looking for like the pairs of electrons. So this is not going to be, you know, um aromatic because it's not going to give you your because we have two double bonds, which means 4 pi electrons, and then this is just one electron that you're adding to it. So, you know, that's going to give you five, uh, pi electrons, which doesn't follow Huckel's rule, right?
Hmm.
That's out.
Yeah.
And then for the carbo cation, right? This is when you're going to have uh like this carbocation is basically like it losing your pi electrons, right? So that's gonna have, this region is, or this carbon is going to have 0 pi electrons,
Mm-hmm.
right? So, um, so yeah, that'll give you
Okay.
pi electrons, right? And that's not going to obey Huckel's rule. And then this one has the 4 pi electrons plus, and the lone pair, the negative charge indicates lone pair, and that means two. So we have 4 pi four of these plus two. So we have six, which is a proper, Huckel's rule number.
Mm-hmm.
So, yep, that's how
Okay.
you go through that.
And then how often do you think like anti-bonding molecular orbital and like the bonding diagrams and like in the passage, how often do you think like that comes up? Like, is that something we should know?
Um, I mean, like it doesn't, you don't, it doesn't really come up like, like you're not going to see like a discrete question that asks you in detail about like, the non-bonding, bonding, anti-bonding molecular orbitals. But you should just know that like conceptually, like if I had like, two atoms like this again, and I have my sigma bond here, um, this region of overlap is your bonding orbital, whereas this region and this region are your
Mm-hmm.
anti-bonding orbitals. So let's say we
Okay.
have a hydrogen with an s like spherical orbital, and let's say it shows up here and donates electron density to this anti-bonding carbon orbital, right? If it adds electrons there, it will like increase the electron density here and decrease the electron density here, and then it can form a bond with the hydrogen, forming a new sigma bond. So essentially, if your electrons are uh, going to be localized in your bonding molecular orbitals, like that forms a bond. If
Mm-hmm.
electron density gets higher in anti-bonding molecular orbitals, it would break a bond.
Okay.
So I would just understand it conceptually like that. Um, and yeah, I don't think they'll ask you anything like, specifically about it, like other than, just kind of showing it to you in passages like this.
Okay.
Mhm.
Uh, okay, kind of like switching gears a little bit.
Mhm.
I have been having some issues with unit conversions
Mhm.
when it's like for this problem, for example.
Uh-huh.
I think it was this. Oh no, 47. Okay, first of all, I like didn't even attempt this problem because I was like low on time. So I like thought that it would be too like
Mhm.
um just take too much time to do.
Yep.
But then in their explanation, it like was you just divided like one thing and it was really easy. Um, so I think that's because of the well, first of all, it was because there was no limiting reagent and I didn't like recognize that. And then second of all, it was dealing with like millimolar, and then it was asking like in milligrams, and but molecular weights in grams. So like I was having issues realizing that like the conversion is much easier than I thought.
Is it like the percent 175 of 272?
Yeah, it was just dividing that. But
That?
I thought yeah, but I thought that like you would have to convert it
Oh,
to grams, but they didn't do that because the original concentration was in millimolar.
oh, I see, I see. So,
So I'm like I
yeah,
don't know, I just have some issues with units. Um
yeah.
yeah.
So, okay, this seems to be involving like stuff from the passage info. Um,
Mhm.
and we have a molar mass here, but we would need to know the number of moles that are being made. Um, so, oh wait, trial two. So wait, trial.
It's trial one is this like trial one and two are the same, but just one was heat or trial two was heated, trial one wasn't. And it said that trial one was 1 millimolar of like both of the reactants.
Yeah.
So their explanation was that you didn't have to find a limiting reagent because it was both the same concentration. And yeah, I just like, I don't know. I didn't even attempt the question
Mhm.
um, because I always assume that these questions take a long time.
Uh, Let me see real quick. So, pyridine functional group accounts directly for the electron carrying functionality of NAD. NAD is an important coenzyme. They tried to synthesize NAD in the lab, and important intermediate for the de novo synthesis of NAD is quinolinic acid, QA. The structures are shown. So pyridine, just a regular, benzene with a nitrogen in it. Quinolinic acid is the pyridine with two carboxylic acids connected to it. So, um, so when we make the pyridine, oh no, when we make the NAD, oh wait, oh no, oh got it. So so they give us quinolinic acid is a reactant in making NAD, and the pyridine is a functional group that's in NAD as well. So we have the structures, cool. Researchers began their synthesis of NAD with an aldol reaction between two acetylpyridine. So like something like this, I think, like two of these guys or whatever, like
Hmm.
groups on the pyridine, and four nitrobenzaldehyde. So uh, a benzene with on the fourth like a nitrogen like an NO2 attached and an aldehyde attached. They discovered that different products were formed when the reaction was carried out at different temperatures. So, trial one millimolar mole of 2-acetylpyridine in 10 mils of water was mixed with 1 millimole of 4-nitro benzaldehyde. Um, to this solution, they added 0.25 millimoles of Na2CO3 and a white precipitate formed. So they're not giving us the chemical reaction, which would give us like, the coefficients and stuff, which would enable us to try to find out if there's a limiting reagent or not. But I guess since they're not giving us that, maybe we don't have to worry about that. So they're giving us this purified product with a molecular weight of 272 grams per mole. And then trial two, they did the same procedure, but they heated the reaction and with vigorous stirring for 1 hour, and it formed, this different colored precipitate that had this molecular weight of 254 grams per mole. So now, since they're not giving us any like chemical reaction, there's nothing we can do to figure out if there's a limiting reagent or not. So I would take that to mean that there isn't a limiting reagent, because if
Okay.
they're not providing us with, the ability to figure out the limiting reagent, I would assume that there isn't one. Um, and so they're talking about 254 grams per mole. And if they are starting off with 1 millimole of some reactant here, 1 millimole of some other reactant, um, okay, um, okay, so 1 millimole of, I believe, should probably be the amount that we end up getting, right? So I think this thing is just to make it precipitate, right?
Okay.
So, oh, I didn't even realize that they gave us a picture of it here. Okay. So we have our, acetyl, or rather, yeah, oh, I drew two acetyls because I forgot this two meant not two acetyls, but the location. So, okay, this is the acetylpyridine. This is the nitrobenzaldehyde, and forms this in room temperature, trial one. Trial two, when it's heated, it forms this, right? So we see
Mm-hmm.
what it looks like, and, okay, so that's what it looks like. So, okay, so. But yeah, it's going to be 1 E negative 3 moles of this times 254 grams per mole to give us the amount of grams uh, that we should be getting. Um, so then this is 254 E negative 3, which is 0.254 grams, which is, wait, what am I talking about here? Sorry. So that'll be point, or wait, 254 grams mole, 254 E neg 3. So that's okay. So that's 0.254 grams, which is 254 milligrams, right?
Mm-hmm.
And then you know, do the percent yield with the 175 that they're giving you. So, so yeah, this one doesn't seem to be uh too much about um like unit conversion and stuff, right?
Yeah. I guess I just like
Mhm.
got caught up with the fact that it was in millimole,
Hmm.
eh, but I guess that like didn't even really matter.
Uh, it it did matter um in that our our in that our molecular weight is 254 grams per mole, but since we have 1 millimole of this, product, right? It means that means so if you have 1 millimole of the product, it means we have instead of 250 grams of the product, we have um 254 milligrams of the product.
Oh, okay. Yeah, I think like just like understanding that if it's millimoles, that would turn into milligrams.
Hmm. Yeah, so I just did like the calculation like normally here. So basically, first we need to figure out how many moles are we making. And since we're using 1 millimole, whoops, of this reactant and 1 millimole of this reactant, our product must be 1 millimole as well, right?
Mhm.
And then I found the mass of 1 millimole of the product to get the 254 milligrams.
Okay.
Mhm. So if you want like a really good like dimensional analysis problem, like I can give you like one or two or something like that.
Yeah, that might be helpful to do like separately so that I can try and like figure it
All right, yeah,
out.
I'll send them to you like then after our like.
Okay, sounds good.
Hmm?
Okay. That was like it for this section so far. And then I had still a couple questions on the last. Mm. Oh, this is kind of like a quick question, but the equation for like the energy of a photon, like HF, is that like frequency the same as like velocity in the speed of light equation? Like they are interchangeable.
Tell me what you asked again.
Like the speed of light equation, like wavelength times frequency, which is normally lambda times v. Like, is that v the same as the frequency in the like photon or like the energy equation for HF?
Yeah, so like the V like new like Greek symbol can make things pretty confusing, so I would just stick to F representing frequency, right? Um and your formula would be like velocity of the wave is equal to wavelength of the wave times frequency of the wave, and that's true for all waves. It's just that for light, that velocity is going to be equal to c, so that's where the c equals, frequency times lambda comes from. So,
Mhm.
and then you're saying related that to.
The like Planck's constant one, like E equals hv.
Mhm.
Like, is that velocity also frequency?
So, the thing that's confusing here is so this v, you're seeing in actuality a Greek symbol called nu.
Mm.
So when you wherever you see that frequency is expressed using what looks like a V. It's really a Greek symbol that means that's the symbol nu. It's not supposed to be a V.
So then in a like in this problem you had to use like frequency and both. I'll pull this one up, but um basically like the problem, I think you had to use frequency in both of the equations and you like it was interchangeable with um loss.
Mhm.
Okay.
I'll be right back. I'm using that.
Mhm.
Okay.
So in this one, the explanation was a little confusing to me. Um,
Oh, so I put an image in the chat, which is like the Greek alphabet, and you can see for N, nu, lowercase nu is that thing that looks like a V.
mhm.
So when you see frequency as B, it's really nu,
Okay.
but that can get super confusing, right? So we're gonna just like even the MCAT like is gonna be using F for frequency. So
Okay.
yeah. So now what we're talking about here is the Doppler effect, right? What can you tell me about the Doppler?
Um, it's based off of like perceived frequency and the actual frequency of um like a wave, and it's dependent on both like the speed of the source that's giving off the frequency and then also the observer if they're moving or not.
So if the distance between the observer and source is decreasing, and that could be either the source moving towards the observer or the observer moving towards the source, you should see a higher observed frequency, right?
Yeah.
And if the distance between the observer and source is increasing, which means they're moving apart from one another, you should see an observed frequency that's lower, right?
Mhm.
And if they're not moving, um, it'll the observed frequency would be the actual source frequency, right?
Yeah.
So we typically think of that in terms of sound, like with like an ambulance or something, but it's true for light waves as well. And that's one of the ways we know our universe is expanding because we can look at planets that are really far away that are supposed to be a certain color, but we see that the color that they appear is red shifted further to the red, and red in the visible spectrum is a higher wavelength. So higher wavelength means shorter frequency, right? Which
Mm-hmm.
means or smaller frequency. So that means that's how we know that the universe is expanding because things are moving away from us, right? So okay, so now this is saying that um optical Doppler effect is used to calculate. Oh yes, this is how a lot of stuff happen, like work. Like my like Fitbit has like a laser underneath it, and also like when they put the you know
The
what I'm talking.
pulse ox.
Yep. Like yeah.
Yeah.
Thing. So okay, let's see. Um, Frequency of light scattered by a blood particle with a speed v is given by equation 1, where f naught is the original frequency of the light and c is the speed of light in a vacuum. Um, okay, and then v, oh yeah, wait, v is the blood particle, right?
Mm-hmm.
Um, and then they made some sensor which can detect Doppler shifted light, and they used a static diffuser, whatever that is, and a rotating diffuser to mimic the flow of blood particles beneath the skin, a laser light with this wavelength. Um, Power of that. So, like, anytime you're given wavelength of light, you should know that if you needed to, you could solve for the energy of that light as well as the frequency of that light, right?
Mm-hmm.
And we're also given power, which means, like energy over time. Okay. Um, so this laser light illuminates a static diffuser as shown in figure 1. Partial scattering occurs at the static diffuser. Um, okay. Um, the remaining light strikes the rotating diffuser. Light scattered by the static diffuser maintains its original frequency, F naught, which makes sense because if the thing isn't moving, like, the light, which is a source of the waves, is not moving, and the static diffuser, I guess, is kind of like the observer, like is not moving, so we're
Yeah.
not having a change here. But the rotating one like does cause a shift, and the shifted frequency is F naught plus delta F, where delta F is the Doppler shift. These two frequencies of light interfere with each other at the sensor. Got it. Okay. For the experiment described in the passage, which graph depicts frequency shift as a function of the wavelength of the laser? Okay. So, um, we first of all know that frequency and wavelength should be inversely proportional, right? So
Yeah.
we look at these like first, like, so like, so this is if it's a constant, right? Uh like if the relationship between the two is a constant, which can't be true because frequency and wavelength are going to be variables. This C is talking about if they're proportional, like linearly proportional.
Yeah.
Um, and then D is if they're exponentially proportional. And then A is if they're inversely proportional, right?
Yeah. I guess I was like kind of confused with their explanation because they were using both of the equations and I just like
When you say
I
both
think.
equations?
Um, mm, like the speed of light equation,
Hmm.
and then
Got it. So
yeah.
this equation here is trying to relate the Doppler shift in the frequencies, which is essentially based on taking your original frequency and altering it by the differential ratio between the velocity of the movement of the particles and c, the velocity of the sound, right? But
Mhm.
since they're asking us in this question about the relationship between the delta F and the wavelength, equation one doesn't have a wavelength term in it, but we should know from this, right, that the velocity of a wave is going to be, the product of its frequency and wavelength.
Mhm.
And this also shows us that frequency is inversely proportional to wavelength. So the only reason that they are mentioning this formula is to demonstrate to you that, or to emphasize to you that frequency and wavelength are inversely related,
Okay.
right? And we can, so like right away, like I would lean towards A because frequency and lambda wavelength are inversely proportional. But
Mhm.
since they are talking about delta F, let's just make sure, right? So we can do some math over here. So like delta F is phi over c times original frequency. Now, this, if this velocity is c, right, I can plug in for c like frequency times lambda, right?
Yeah.
So this can be like velocity over frequency times lambda times your original frequency, right?
Mhm.
And so this frequency here is going to be the same as that of the original frequency, right? So that
Yeah.
cancels. And now we see that delta F is inversely proportional to wavelength,
Okay.
right? So this involves us first knowing, or we first must know that frequency and lambda and wavelength are inversely proportional. Higher wavelength, lower frequency, higher frequency, lower shorter wavelength. So, and we see a linear proportional relationship, an exponential proportional relationship, constant, which isn't a relationship, and an inverse relationship. And by the way, inverse relationships don't look like this. They look like this, hyperbolic. I don't know if we talked about that, but you know, an inverse proportion is like A is inversely proportional to is one is proportional to one over B. So,
Mhm.
B can't be a zero. So these axes are asymptotes, so it turns into that shape, hyperbolic.
Okay.
So yeah, first of all, you should know that frequency and wavelength are inverse. But then using this formula, you can plug that in, like C is equal to frequency times lambda. You can plug in that for C to get frequency times lambda down there, and then the frequencies cancel, and then you get your delta F is equal to V over wavelength. And you can then see, like, officially that delta F is inversely proportional to wavelength.
Okay.
Mhm.
Yeah, I think like I was getting mixed up with that equation that they provided and then like the energy equation because that has like it has frequency in it. So I was like, I
Yeah.
don't.
So once you start to talk about energy, that's when you're going to introduce Planck constant. Okay.
Okay.
Um, so, and even with that, you can do like, energy of a photon is hf. If you don't have frequency, though, we know from C equals lambda times frequency that frequency is C over lambda. So for the F here, we can plug in C over lambda. That's how you get your other expression for energy for photon.
Okay. Um, yeah. Then I had one more, I think, that I was a little confused on.
Yeah, and get into and I would just like no longer use V for frequency because that's gonna make things super super
Okay.
yeah.
Yeah, it definitely was making me
Yep.
confused
Yep.
and
Yep.
frustrated.
Yep.
Um, okay. This one, I guess going over why um the entire nitrate molecule is I think the correct answer was saying that the nitrate is getting reduced, but is it getting reduced because the entire molecule is losing an electron? So isn't the nitrogen getting reduced? Like that's why I was confused because the molecule is losing an electron.
That little spot there must have had some really turbulence if they routed around.
I see what you're talking about. Yeah, I think they're and when they say the nitrate, I think they're referring to nitrogen.
Okay. Yeah,
Um,
because I wasn't sure if it was me misunderstanding a concept or if like they just
yeah,
labeled it wrong.
yeah, I think that's the case. It's because it's not like the entire nitrate, is gaining electrons. Um, right? Uh, yeah.
Like if it's saying NO3 minus, which is turning into NO,
Hmm.
is the NO3 minus losing an electron or are they just like completely two separate molecules, you know?
Uh, so I guess if we look at the entire molecule, it's like the nitrate goes from negative to, well, we don't have nitrate anymore. We, it turns into nitrous oxide, which is what they use in like Fast and the Furious and stuff. So, but yeah, no, I see what you're saying. Yeah, they messed up here. So yeah, here we see that um yeah, oxygen should have -2, so multiply that by 3, -6, and overall negative charge, so the nitrogen should have a +5 charge. And then for the nitrous oxide, the oxygen's still -2. There's one of them now, so the nitrogen is going to be +2. So from here to here, the nitrogen, not the nitrate, the nitrogen gains electrons. So yeah, they messed up.
Okay. There was also a question on the one I more recently took where the answer was that both were getting oxidized. Right? I didn't know that was possible that two things in a reaction can both be oxidized.
Um, were there two things getting reduced or something?
I don't remember, but
Okay.
I think it was like NADPH to um NADH, and then it was or NADP
E?
plus. I don't know. I think it was like NADP plus.
Uh-huh.
And then the like reactant to the product was also being oxidized.
Mhm.
So I just didn't like understand how that's possible.
Uh, got it. Yeah, I guess we'll see it. You have it.
Yeah, I can try and look at the question. I don't remember what it was. Um, yeah, I don't know. I mean, I have a feeling I'm not gonna be able to find it,
Okay.
but um, yeah, I don't know. I still kind of get mixed up with like whether something is reduced or oxidized sometimes.
Uh-huh. In in what
I
sense?
guess like
Mhm.
the like in the case of like NADPH to NADP plus, it's losing a it's losing electrons, but isn't it?
So in Gen Chem, redox is like this problem that we just did, where like oxidation's loss of electrons, reduction's gain of electrons, and we see changes in oxidation state for specific elements, right? But in like biochem and organic chem, um, I have like a biochem redox PDF in the shared folder, but that loss of electrons, gain of electrons is kind of useless in biochem reaction like redox. So for that, I would look at mainly three things. Like oxidation will involve either loss of hydrogens, gain of oxygens, or gain of bonds to oxygen, right? So like NAD plus to NADH, right? So what we're doing here, so like what are we okay, so are we is this an oxidation or a reduction?
It's a reduction.
Okay. So that means that it must be gaining the NAD plus is gaining uh an electron, right?
Yeah, but it like isn't it technically also gaining a proton?
Yeah, it'll technically also involve this, right? But the question is like how can it go from NAD plus to NADH like neutral if you're adding hydrogen to it, right?
Yeah.
And the answer is you're really adding a hydride, which is a hydrogen with two electrons instead of one, which means it's a negatively charged hydrogen. So you're adding
Oh,
the electron in the form of a hydride, and so that's going to get you NAD plus to NADH. That can be with also the H plus. And yeah, for NADP, it would be NADPH. So, uh, so basically,
okay. And well, that was like kind of my last question, I guess. I still have to do bio because I don't know. Bio, I was
yeah,
like pretty disappointed with because I dropped 2 points for that one when usually like I'm better in bio than I am with chem. So I kind of have to figure out why that happened.
it's probably yeah, because like the bio passages can be a lot more like dense and just full of lots and lots of like acronyms and terms and really, really hard to decipher like um graphs and charts, right?
Mhm.
So when reviewing your BB section, you want to be able to, I mean, I know you do this already, like when you write down, the reason you got things wrong. Uh, but yeah, you want to look at like, if it's primarily because of like, misinterpreting what the passage is saying or like overlooking what the passage is saying or having a hard time like interpreting a graph or a figure or a chart. That can also contribute to it perhaps taking longer, uh, which means that you're going to run out of time sooner, which means that you're going to not have enough time to answer certain questions, and that might lower your score.
Yeah.
So yeah, I feel like it's going to be like passage stuff.
I've like, even though I have been using my whole sheet and like filling out everything, I'm still kind of having trouble figuring out what kinds of questions are really giving me the most difficulty. Like I'm having trouble piecing together the underlying theme in all of them.
Mhm.
And I'm not sure why, because
Yeah.
I'm like writing down
Yeah.
stuff and like trying to remember my thought process. And I know like there's, I tend to have more difficulty with questions that I have to analyze a table
Hmm.
and the graphs more. But then there's sometimes where like I'll be missing little things and I don't know why. Because I think I'm like paying attention pretty well and then I'm not. And then like I've been noticing that with the like sections that I feel less confident in, I end up doing better. Like I felt pretty good about the biochem section this time, and I ended up doing like a lot worse than I thought. And then it was like the opposite with chem, where I like flagged like half the test
Yeah.
basically, and I did better than I thought.
So, I have your practice questions like thing open. Um, where where should I look for like the BB? Like I know there's a BB tab, but
Um,
like the most
well, in
test or whatever for
Well,
BB
the most recent BB was last week. If you just like scroll all the way down to the bottom,
of the BB
um, yeah, yeah, it's labeled um on January 23rd.
um oh yeah. Okay, okay. Let's see.
Like sometimes I'm able to pick out common themes of like content gaps, but I don't know, like I'm just kind of maybe I'm like writing things down like not in a efficient way, but I'm still just having trouble like really figuring out why I'm like missing like keywords
Mhm.
or like if it's because of the passage or like I'm spending too much time reading the passage.
Yeah, I see a couple of things that say like missed key concept in passage, missed point due to knowledge. Oh, I guess that would be content. But missed key concept in passage. Um, Clarifying two types of experiments, drug experiments and wild type, learn how the variable drugs so negative. Um, Researcher separating. Oh, and then it kind of ends there. So passage understanding. And then I see something that just says like mistake.
Oh, that was probably like a dumb mistake.
Okay. Yeah, so okay. When we meet next, we can go over like the ones that you wrote, like either like mixed key concept and passage, or something like passage based rather than like content based stuff. Um,
Yeah. Do you think I should be like when I'm labeling things, should I be like more specific with I mean, I don't know. I'm just like not sure why I'm like unable to say like I have to work on this thing specifically because I feel kind of like all over the place. And then the fact that I'm like still not really seeing a big improvement is like frustrating too.
Yeah.
And I don't know if that's like I have to keep doing like flashcards for content or it's like a strategy issue.
Yeah, so of course, every test that you take, you will learn new content for. So every time you're gonna take a test, like yeah, you're gonna learn content after that test. Now, for the ones where it's more like like something in the passage is what threw you off, that's like what we can go over when we like, meet. So I would say like uh I guess like from like today, for instance, like when we went over some of these questions, like I was kind of describing to you like for that like Huckel passage or whatever, like about how like I guess I was like kind of thinking out loud to kind of show you like the reasoning of
Yeah.
how to like approach these problems. So like yeah, so like for the most part, like the ones where it says like missed key concept in passage, or one of them says like not using the equation used in the or given in the passage, should look at equation even if you're logically reasoning. So like so yeah, I would have, the ones that you got wrong or had a hard time understanding, um for or mistakes that are not due to like a content gap, that's what we can look into. So I would say for the next time, why don't we have you choose like a passage um that you found particular that you a passage in which you've gotten the questions wrong, not due to content gaps, but due to not like understanding the passage or not understanding like the passage as a whole or like elements of the passage or graphs or charts or
Okay.
figures and things like that. That'll help us, kind of narrow it down and kind of like focus on the um strategic kind of aspect of the test.
Yeah, because I think something that's been happening is that I'm reading the passage and I'm trying to understand it, but I'm also just trying to read it to get through it so I can move on. Because I'm really worried about the time issue.
Yeah, so I mean, it's easier said than done, of course, but like I always say, like slow is smooth is fast. Like if you want to get good at something, you do it slowly, like kind of step by step. And after you do that with enough, practice and repetition, it starts to become you like internalize it and it starts to become something uh that becomes instinct. So
Mm.
because this is like the most, common problem that people like talk to me about. It's like if it takes me, it's like let's say we go over a problem and I kind of show that it's gonna take some time to figure out how to answer this problem correctly. Um, and then we go through it and we get it. Usually students say things like, okay, that just took a lot of time. If I can't do it now, how will I do that on the test? Right?
Yeah.
That's like what everyone asks. But you now will not be the same person when you take the test. When we get to that point, you will have done like learned all of these things um, without worrying about the timing aspect of it because you prove to yourself that you can figure out the answers. So for like the ones where so I'm guessing like questions that are like have the green background are ones that you got right on the blind review,
Yeah.
right? And the ones with the pink like aren't.
Yeah. The ones
Mhm.
the red ones are ones that I got wrong both times. Green is it was wrong when it was timed, but I got it correct after. And then I don't even think, oh, then orange is like I got it right when it was timed and then wrong when it was untimed.
Mhm. So
Back when I was like doing the whole test over again.
yeah, yeah. Oh, yeah, yeah, yeah. So yeah, so like honestly, it's gonna yeah, it's almost like, counterintuitive, but like the secret is like, and also to like be a little like more like, I know like people take this test to get into med school and people study for the test so that they can do well on it, but people who usually do well on a test like this or things in general are a lot more like process oriented. So if you kind of just let yourself trust the process that you're learning, um it can really help in terms of your mindset, because if you're going into it kind of with the attitude of like, okay, I like, let me just get through this, so I could just, whatever, get
Yeah.
some score on it. Like, it's going to always feel like a slog. It's not going to be fun, and each time you take a test, like, if it's not like, you can even score like high on a test, and if the next test is like 2 points lower, people a lot of times like, especially on like Reddit and stuff, like would just be like, oh, like what am I doing? Like eh, it can affect people a lot. But I would say don't let any like particular test affect you too much, because every test that you take, you're learning from. And even if your score isn't going to be increasing, which is super like common, like that's basically what I found when I did all the when I brought all the data in for all the different practice tests, and you know, for people who scored like 523 or higher, it's like the Blueprint or Altius tests are just like pretty much around the same score, like not seeing linear increase. So you don't necessarily need to see a linear increase in your scores, because think about all the other stuff that you're building. Like compare like, let's say, how your stamina or something, right? Like the tests that you take. So you've taken like, I think just like three tests, like practice tests, right?
Um,
So
no, I took the Kaplan ones too.
got it, got it. So like think about when you first took your practice test, like how like when you finished it, you were probably super drained, but as you took more and more practice tests, you know, do you feel less drained afterwards? I guess it depends.
Yeah. I was like honestly the first one that I took, I wasn't as exhausted after as I thought I would be, but I definitely like couldn't really do more work after.
Yeah, yeah.
But like yesterday I was interested in seeing like what happened with cars, so I ended up like doing the blind review after the test yesterday.
Yeah, yeah. So I would say that, we're going to have you take a lot of tests. I think something like 14 or something like that. Uh, so like you're just going to get better at the tests, even if like, you will probably see score improvement and stuff, but even if we don't, like you will definitely be able to like compare now to like 14 tests from now. Like the amount of, energy and focus and stamina and endurance and psychological factors and all that stuff that drains you whenever you take a practice test will become less draining as you take more and more practice tests. So these are kind of like, the hidden curriculum kind of thing, which is like a psych social concept. Like, so yes. So I would say that to try to focus more on the process, on the fact that you're learning every single step, regardless of the scores that you're getting. And that with more and more practice, you're just going to get better and better. And even if that doesn't translate to like an increased practice test score, uh, it's going to be less tiring. You're going to feel less tired, less fatigued from doing, these problems, from doing these tests, you know? So
Yeah.
so I would say that no matter what, you are invariably improving. And like, if things take, it's okay for things to take long now because, and you don't want to think, okay, if it takes me this long now, how am I going to have time on test day, right? But I rarely ever see people like start off doing things, like timed that do well eventually when they take their test because when you start off doing things timed, like if you didn't do the blind review, like there's going to be so many questions and things that you never get to answer. And
Mhm.
and so you want to like it's a critical thinking test, so you want to be thinking as much as possible. So like if you're doing a passage or a question and you like imagine like your brain like lighting up and stuff, like that's what you want. So and you'll see it with like I'll send you like some questions, those questions for like dimensional analysis. But um but yeah, so ultimately I would just say that not to worry too much about what you're eventually going to get, but to be process oriented. Um, think of this test as being like the end goal rather than a step in your overall goal of becoming a doctor. So that way you can kind of trick yourself into, you know, feeling more, I don't want to say like excited by it, but not as like you don't want to think about this as like, like it's just something I have to like suffer through so I can just get to med school. So I would say,
Yeah.
yeah, the process, um, allowing things to take a lot, like it's okay to be slow when you are figuring out problems at this stage. And and yeah, by the end, we're gonna have you take like so many tests that a lot of these problems will autocorrect.
Okay.
And I guess for next time, we can you can show me like a passage, and like it might be hard for you to pinpoint exactly what issues you're having with the passages now, but when we go over one together, like from BB likely, I'll be able
Mhm.
to kind of see like what like how you're analyzing the passage, how you're taking in the information, how you're separating what matters from what doesn't matter. All of these things are going to come together at the end.
Okay.
Yep.
Sounds good.
Yep. So I'll send you a couple of questions and yeah, take as long as it takes. I mean, like I remember when I was studying for this test, like I would like if I spent like an hour on a single question, like but I still got the answer right, it meant a lot. Like I knew that like the fact that it took an hour was nothing, like it wasn't a big deal in comparison to how much I learned from figuring it out and coming to that answer myself. So yeah, that's what I would say. So all right, so I guess I'm seeing you what next week?
Next, I think there wasn't a time open next week, so I signed up for like Monday of the following week.
Uh-huh. Yeah, I have some
Yeah.
openings. Um, but I guess it depends on your hours as well. Like for instance, Wednesday I have like at 7.
I can't do Wednesday. I have work.
Uh-huh.
But I was planning on, that's another thing. Like I'm assuming that I'm taking another practice test next week. Um, so I would either be doing that Thursday or like maybe Friday even.
Mhm.
Um, yeah. So maybe it's like better to have the next session on the next like Monday anyways because I do work this week.
We say Monday